Hello. In this lecture we're going to discuss traction force and slip control. That is the control that is done to obtain a certain tractive force or tractive effort and the corresponding slip control. That is related to what we did in chapter 2, but now we'll look a little bit more into the control itself. Well, the traction force control is designed to obtain a certain tractive effort or traction force independent of, as you can see here, speed changes, varying load and disturbances. The disturbances, they are typically due to varying line voltage. It can be poor current collection, that is, we have problems with the current collection, insufficient adhesion, or a varying running resistance. It might seem that varying running resistance is a disturbance. It might seem strange, but from control point of view, this kind of varying running resistance is treated as a disturbance. This traction force control is what we call a dynamical system, a dynamic system. That is, the output depends on the input, but also of the present state of the system. So it's not only an input-output system, it's also depending on the state of the system itself at a certain given instant. It's a mix of what we call a service system and a control system. A control system is where we try to control a parameter or some kind of variable to avoid a fault, that we reduce the fault down to zero, then we have sort of perfect control system. A service system is where the output signal follows a certain input signal. That is not specifically to avoid a fault or to reduce the fault to zero. It's following an input signal. Whereas, as I said now, the control system is to control system in such a way that the error is minimized or zero. What we are working with is the adhesion curves of the trace, and this is a poor figure. We have some problems with the Macintosh translation of the input files, but this shows the friction mu. This is 0.4, 0.3, 0.2, etc. And this is the creep dV as so the overspeed of the wheels. As you can see here, there are two typical conditions. This is for dry conditions, where you have a very clear peak and a rather steep derivative from zero up to a certain given value. This lower figure shows more poor conditions, wet conditions, slippery conditions, where the friction is increasing but without any clear peak. This, of course, creates different conditions for the control system to operate under. This is good friction, and this is poor friction. So there are several factors that influence friction addition, and in addition to the slip speed. Of course, weather conditions and contamination. That might be dirt, ice, rust, oil, leaves. So if it's different humidities, might as well influence the possible and the friction you have between the wheel and the rail. To the right, we see a typical figure that shows the friction in reality. In reality, you have no very clear and well-defined relation between overspeed and friction. It varies all the time along the track, and that more like a stochastic relation, that you can get any kind of value. So in reality, you have to face friction that is varying all the time, and you have to have a control system being able to handle this variation of friction that is not as perfect as it looks in the theoretical textbook. Adhesion is also influenced by vehicle speed. Typically, adhesion is dropping, is reduced a little bit with increasing speed. As you can see sometimes in the tractive effort diagram of a train, below base speed, instead of having a very straight line, you have a slightly decreasing value of the maximum tractive effort for increasing speeds, and that is an adaptation to the fact that adhesion is reduced by increasing speed. Of course, the condition of the tread on track is also important. If you have new tracks or worn out tracks and the tread is in a different condition. So let's look at some of the system characteristics for this kind of control. Typically there are two parts. One is necessary conditions. That is line voltage available, cooling functioning all right, is the control voltage is in order, all these kind of conditions that you have to fulfill before you start operating. And the second one is the dynamic control itself. That is the control we have described so far and will describe now. When you look at the system, there are, of course, several different parameters you have to look at, but two important characteristics are the accuracy and speed. Accuracy is, of course, improved by improving the measurements. How accurate can your values be? The second is speed in the way that you have a fast rise time, and the rise time normally depends on the amplitude of the control signal. If you're going to control a current, you need to apply a high voltage or a very clear, at least a significant voltage to be able to control and change the value of a current. So how fast you change the current depends on how big the voltage is. In the same way, so of course any control signal and the effect of that control signal is depending on the amplitude of the control signal itself. The second part of the speed relation is, of course, the settling time. How long does it take until we reach some kind of steady state? Another important difference between different trains is the converter bandwidth. Different converters in different trains have different bandwidth. And let's compare, for instance, a thyristor rectifier locomotive with DC motors, typically described in this textbook in Chapter 6 and in Chapter 3. In that case, you have a line commutated rectifier, which means that you have, let's say, for 16 and 2/3 Hertz, you have 60 millisecond cycle time, period time, and you have 30 milliseconds between each time you can do some kind of action. You can change the triggering angle alpha every 30 millisecond, which of course generates a pretty low bandwidth. In a modern propulsion system with voltage source converters, you're typically operating with a much higher switching frequency, which means that you have more possibilities to change the characteristics of the system, to control the system. Let's say you can have switching frequency in the range of kilohertz, and of course that provides a much higher bandwidth, better controllability than it did for the DC motor thyristor locomotive. Historically, measuring of slip speed has been one typical electric traction problem. If we want to have a correct slip speed, we can of course measure the speed of the wheels, but we also have to estimate the true speed of the train, because the wheels are always sliding a little bit, both when we're braking and when we are motoring. So we cannot just measure the speed of the train by measuring the speed of the wheels. We have to estimate the speed by some other means. And that is also a very typical classic problem when it comes to creating a certain traction force. One example, one possibility would be to have a measuring wheel or some non-powered wheel in the train that doesn't slip. And that is of course possible to have if you have a multiple unit train where not all the axles are powered. Then you can use one of the non-powered axles to estimate the real speed of the trains, an axle which is not sliding or slipping. You can possibly reduce the tractive force of one of the axles. In that way you try to ensure that that axle doesn't slip. That would, so to say, give you a better estimate of the true speed than if you're trying to get a certain tractive force from that axle. You can estimate the true speed based on train weight, tractive force, and expected acceleration. You can make models of the drive system, propulsion system, and the control, including all these kind of parameters you want to find out. And from that model, you can estimate these values. And in that way, you can also estimate possibly the true speed of the train. That is typically used in many modern or advanced traction force control systems. Other possibilities are, for instance, Doppler radars, some kind of correlation measurements. And of course, today you can use GPS. That is, of course, one of the most obvious ways of getting a true speed of a train, as long as the accuracy is good enough. Of course, it does not always work. It doesn't work if you have tunnels and in subways and so on, but it works for many trains in normal operation. And perhaps you can have some other means of measuring the true speed in tunnels, for instance. This figure is also a little bit poor. It shows two different strategies. You have track force control and you have slip speed control. And track force control means that we want to get a certain adhesion. We want to ensure that we can get a certain track force all the time. And that is controlled in this direction. If you have poor operating conditions, if it's slippery conditions, for instance, then this track force control might not work because it might generate overspeeds or slip speeds which are too high, creating a lot of wear on the wheels and on the track itself. So in that way, it might be better to have some kind of slip speed control that is determined that we are operating by a certain slip speed, and in that way limiting the possible tractive effort you can get, but also limiting somewhat the wear of the track and the wheel. That was the end of this lecture.